Good morning.
Good morning, Professor Fish. How are you?
I'm fine, thank you. Yes. I received an email from Dr. Sobchak, but I have to admit I haven't had a chance to read through it yet. So.
Review the document that he sent.
Yeah, no, I haven't read it yet. But good morning, Dr. Sobchak.
Good morning. Good morning.
Oh, good morning, Professor Garrett. How are you?
Good. It's raining outside. It's pretty miserable weather, but it's
Thank you for sending the document that I received by email yesterday from you, Dr. Sobchak. I have to admit that I haven't had a chance to review it yet, but maybe that's something that I think that you were intending to tell us about today.
Well, I'd like to talk a little bit about it. I've got over some of this stuff before, but there are some new results that I think are pretty interesting about which I'll. But of course, I'm interested in more with the graph theory. I was going to work more on the graph theory stuff, but I got started on this calculus stuff, and I was able to do more with that than I have with the graph theory. But I think there must be a way of applying these new tools to graph theory, which is, of course, what I'd like to explore more. So I'm willing. I'd be very happy to hear what Dr. Cruz has to say about graph theory more.
I was on the title of your paper. I was curious to see that you emphasized a calculus as opposed to algebra. So I was interested to find out what you meant by that, as opposed.
Yeah, basically, I'd like to talk about the gradient operator, the Gibbs Heaviside vector analysis, which is extended to geometric calculus. That's all it is, really.
Ah, I see. Yes.
And also, I developed a new formula relating the geometric algebra of Euclidean space to the Lorentz metric, which is interesting to me. A very interesting formula. So I can show you that without even going through the rest of the material, since in a way, the rest of the material we've gone over before, but you can see how the geometric product between Euclidean space and the Lorentz metric are very closely related. The Lorentz metric in higher dimensions is extremely close to Euclidean geometric algebra. Just a couple of terms, which I'll show in a couple of slides there.
Okay. Dr. Cruz, did you have something you were going to present to us this morning?
Yes, sorry, because I started Zoom in my other computer, but it's asking to me to update. And then and I am going to try to present with only this equipment that are connected yet, and I hope it works. Okay, then.
Okay.
One moment, I'm going to look for the file. No, not yet. Sorry, because but I have some problems here with the file, and it is not actualized yet, and then
Perhaps if you think that it would be better to complete the update of your other computer, then
yeah, yes, I am trying to update the Zoom of this computer. And then, okay. is the problem with this system, because some not start if you do not update before, then it is not possible to work with all the version. But now is installing in my computer. I think this not take too much time.
Okay.
And the principal idea of the document that I prepare is only to go inside the relation between category theory and graph theory. This is the principal idea. There is not too much, but this gives to us the opportunity to approach at all the power of category theory for working with the problem that we want to study. Then I think that in fact, maybe some words about the category theory first is that in the process of building a category, we start with the graphics. And in fact, like McLean showed in his book of category theory and the working mathematician, he started presenting first a metagraph. The idea is to take one abstract concept about the graph first, and in this way, with the definition of metagraph, he presented the theory of meta category. Then I think now is finished. Oh, okay, finish yet my other equipment. Then okay, I am going to share my screen. Okay, here we have okay, I am using the presentation that we discussed the last meeting. And before I have here some definition about the properties of graphs. The principle of these are paths and cycles in a graph. And with this, if you remember, we present the different kind of cycles that we can have in a complete graph. I'm going fast here in the way of not present the ideas with one background. Another kind of important graph is the opposite graph, related with an graph only changing the direction of edges. It is important because we change the two functions that are used for build a graph, changing the source and target functions in the opposite way. That is first target and after source. Then this is an important idea because we are to find this after in category theory. Okay, and then here there is an illustration of the opposite graph in a different kind of complete graph. Then how you can see in the graph of in the complete graph of 3 degree, we have this kind of opposite graph that are part of all the relations of in the complete graph. Then it is important because we need to analyze in different way these two types of graph. Then we can see after, later that here we have one kind of relation, and here we have the dual of that relation. Then in a complete graph, the idea of duality is present in the building graph. Okay. Then and here we have the representation of that complete graph like a tree. Here we have the definition of a tree that is connected, that is a cyclic, and have n-1 edges. Then with this idea, here I present the tree graph for a complete graph. How you can see, and this is a term suggested by Professor Pesch, we have a tree and a co-tree related. Those are opposite graph that can be used for presenting different kinds of operation here. For example, if we take the first left arrow in this graph, then we can go back by going by in this way or in this way. Then we can have a cycle. The cycle here in the tree graph is wielded going from this node to this node. This is the root of the tree, and using the some ideas, this is a core root of the tree. Then we can get a cycle going from this first order edge and going back by this way, or in or going in this other path. In fact, we are describing paths on the wielded graph. Okay, then okay, then those are different degree graph of complete graph. Here only the important idea is that we have a operation of grafting, and this operation of grafting permit to us to take the lower order graphics and by the grafting process to build a higher order graphics. Okay. And then we go to the binary relations. First, here there are some elementary definitions about relations, but the idea is that direct graphs are isomorphic with the binary relations. And then it is too much important, because if we work with direct graph, then we can present all the properties of binary relations. And then we can go to binary relations and direct graph. And in the case of binary relation and directed graph, we have those properties: reflexivity, transitivity, and reflexivity includes loops at every vertex. Symmetry are this mean that are undirected, and then this is related with the complete graph, and transitivity to that two vertices in edge of the disjoint graph are adjacent. Then all these properties are properties of a complete graph. Okay, and then we start here with the axioms for a category. All these ideas are taken from the book of MacLean, here cited. Okay, then we start with the idea of metagraph. The definition says that it consists of objects and arrows. Like in graphs, it consists of vertex and edges. Then these two ideas are related. Then here the vertex are called objects and can represent any kind of class of object, and the arrows can represent any kinds of relation between objects. Then the way of building a metagraph is defining a domain and a codomain. If we take two objects, then the domain of one arrow is one object, and the codomain is of that arrow is another object. Then with this definition, we can present this idea with this expression. If the arrow F act on A and take the object A like domain and then arrives to codomain in the object B. This is another alternative representation of this metagraph.
Jesus,
Yes.
it might be worth mentioning the use of the word meta here. Like why you might wonder why is this called a metagraph instead of just simply a directed graph? And if I recall correctly, McLean was concerned about the situation in which the collection of objects do not necessarily form a set. So
Yes.
So if we said that the objects formed a set and the arrows formed a set, then a metagraph would be just a graph.
Yes. Yes. Yes.
So
Yes.
it's kind of, the word meta is a kind of a technical issue.
Yes.
Right.
Yeah. And we can say that the idea of using the word meta before graph is to say that we are not considering only sets, but we can consider any kind of a class of objects and any kind of relation. And in this way is that we can use the word meta here. Yes, and I don't know, but maybe in Burroni, I think he don't use the word meta, but he used the words universals, and with this idea of universals, he presented the concept of category from this. But I prefer the presentation of McLean. Okay. Okay, here we continue with the action for category. And then after of defining a meta graph, we define a meta category. In the same way, we can say that we use the word category when we speak about a category over the sets, over sets. Then that is taken like objects sets, and taking in like arrows the functions between sets. And this is the general idea. But here we use the word meta category, and then the principal idea is that with that definition of a metagraph, we add two more operations, and these operations are identity and composition. Then for in the way that we can speak about a category, we need these two operations. And the definition of identity is that the relation, we can establish a relation between objects and these relations take the object like domain and the same object like codomain. This is the principal idea. The other operation is the operation of compositions that takes a pair of arrows, and with this pair of arrows relate one a new arrow represented by G circle F. This pair of arrows are assigned in this way. First, the domain of G is the codomain of F. This is the principal property in this operation. Then the circular operations only take the domain of one arrow and assign this like a codomain of the next arrow. Here is a graphical representation of this definition. Here we have the arrow F and the arrow G, and with these two arrows, it's assigned the arrow G circle F. It is important to note that the first arrow that we write are the arrow that is applied after. This is frequently problem with this definition, but it is important to note this. Sometimes it is speaking in this way. First F after G. In this way is in the lectures of this relation. Okay, those are the principal operations, the two additional operations that are defined in the way that we can get a meta category. And then here, in the way that we relate this with the prior definition of graph, I am here presenting an extended graph that are representing the composition operation. The idea of the extended graph is that this implies one order, first A, after B, and finally C. Then in this way, we've applied first arrow F and after arrow G, and it is equivalent to apply the arrow G circle F. Then this is a relation that maybe can think that it's only a different way of drawing this picture, but I think that this permits to us to relate for a complete graph this kind of operation. Then we can speak in general about compositions in these arrows that are part of a complete graph.
I have a question if I can.
Yes, Professor
Ask it.
Garrett. Mhm.
Yeah, I'd like to, are we using graph theory to do calculations in category theory, or category theory to do calculations using in graph theory? I'm just interested if we're actually using graphs to be the algebra of category theory or something, or is it the other way around? I'm trying to understand the relationship exactly between category theory and graph theory, or algebra, and the relationship between these different languages, if you want to call them that.
At the end, we can say that here in category theory, we use a graph for representing this kind of operations.
So that's kind of an algebra then, that we're using graph theory to serve kind of as an algebra of category theory, almost, it would seem. Is that completely wrong?
You can see that, okay, first we can say that in short, we can say that category theory use graph for representing the properties of this class of objects. And this class of objects have relation between them. Then we use graph for representing this kind of properties, and graph are too much useful in category theory, because we can see in a graphic way this kind of property. For example, here, the composition operation is representing with this graphic, and then I think that it is easy to understand the properties of this. You can see here the order of application of this relation and how you can get one equivalent relations related with these two. It is important that not even that we have two kind of arrows, we are going to get an equivalent arrow. It is necessary that the composition operation be defined for this pair of arrows. And
Okay,
then,
so the category theory is actually the arrows, and whatever in the graph theory is just a representation of the relation in a category, then, like in category theory, or a particular category. I guess we're talking about all kinds of relations, and that a graph is just a description of the structure of categories, I suppose is correct to say.
I suppose that we can use in this way. I don't know what are your opinion, Professor Pesh?
Well, I would say that every category, underlying every category, there is a metagraph, right? That if we have a category structure, then we have these two operations that Jesus just mentioned, identity and composition. But if we forget about those two operations, then what we have left is technically referred to as a metagraph. And it, in every respect, is like a directed graph, except that we omit the requirement that the edges and vertices form sets. So the fact that they don't necessarily form sets makes a metagraph something a little more general than a graph. but only formally more general. So it's a matter of placing emphasis on the axioms and specifically omitting any reference to set theory axioms. Like we don't want to insist on the formation of things being sets, because ultimately we want category theory to be relevant where we cannot define things as sets.
Of course, you could talk about the set of all categories. Is that
no?
incorrect? No, you can't.
No, that's incorrect, right? You can say that a set, sets can be objects in a category, in which case the morphisms are mappings between sets. But at no point do we insist that the set of all sets is a set. So in other words, the category of sets, the number of objects in the category of sets is too large to form a set.
Okay, it's like
this is kind of a logical contradiction that people like Russell and so forth were deeply concerned about the fact that mathematics up to about 1900 or so was presumed to be that it could be founded on, that all of mathematics could in principle be founded on the theory of sets. But Russell and a few others showed that couldn't possibly be true. That this sort of caused a crisis, formal crisis, especially in the sort of philosophy of mathematics.
Yeah, that's Gödel's ideas, I believe.
It's related to Gödel's theorem, yes, related, but it's a little deeper than Gödel's theorem. Gödel's theorem has to do with the decidability, and so it has to do with the existence of algorithms that can formally prove something or not. Whereas Russell's paradox is sort of a logical contradiction that occurs when you say you would like to consider the set of all sets.
Yeah, I get that. Yeah.
So if you
how
try
about the set of all ideas?
well, maybe that's also a similar sort of Russell type paradox, because an idea, the idea of a set of ideas is an idea, right? So that means there are too many ideas to form sets, right? Anyway, but graph theory, generally speaking, the people who studied graph theory formally started before the 1900s, and so they started with the presumption that the vertices formed sets. That was a presumption that they thought it was sufficiently general. But for the purposes of category theory, Sanders and MacLean, for example, who were sort of one of the founders of category theory, were concerned with avoiding this paradox that Russell had pointed out. And fundamentally, they wanted to start over and define a new foundation for mathematics that avoided the problems that Russell had identified.
And this is category theory.
Yeah, so from that point of view, category theory is a very foundational subject in mathematics. It's a language. It's a logically consistent language in which to formalize all of mathematics, in the same way that it used to be believed that set theory could be a formal system in which to do this.
Okay, so in a certain sense, graph theory is large enough to represent ideas from categories. For example, in this simple slide that De Jesus has presented here.
Mhm.
Now-
Well, to use your example, we in category theory we can allow A, B, and C to be ideas, and so that the morphism F that relates the one idea to another idea, is an allowable object in category theory.
Okay, but it's not allowable in set theory, as we just discussed.
Yes, exactly, right. So therefore, this notion of meta is just emphasizing the fact that we're only taking sort of as foundational the two operations that it uses defined previously, that is dome and codome. So as long as we have an operation called dome, which for any arrow tells us what is the domain of that arrow, or associates an object.
Okay, and the other idea is the code domain, and that's just reversing the arrow then, representing that
Well,
idea.
Domain is the source of the arrow, and codomain is the target of the arrow.
Yeah, and then you tie it together with the idea of duality.
Well,
Not yet.
one kind of duality is just exchanging. Every time you have a domain operation, you replace that with a codomain operation, and
Yeah.
vice versa.
Yeah, I can see the problems of, like you say, the problems of set theory, why category theory was invented to try to get around those problems.
Well, for example, in category theory, we often would talk about, say, the category of rings. So that means the objects are any ring. So formally, abstract, algebra, we define what we mean by a ring just in terms of its axioms alone.
But you wouldn't
But
say the set of all rings, even though.
No, that would be incorrect. Type A be incorrect type. Yes, that's.
Okay, that's interesting.
Sometimes the distinctions are just formalities, but they're fundamentally important if you're concerned about the underlying logical.
So you invent graph theory in a certain sense to do certain calculations in category theory, but it's just it's like a way of drawing pictures as you draw in for graphing functions and so on, but for using graphs for abstract concepts in category theory.
But the idea is that you can get one picture of the property of that object, and then you can understand better that property and apply for concrete calculation.
Okay, so what I'm trying to do, of course, is use geometric or Clifford algebra to represent ideas in graph theory, or relationships between vertices and edges and so on, using geometric algebra. So of course, it could also be applied to the same problems that such graphs are applied to the ideas of category theory as well. Then, kind of a.
Well, let me emphasize one more point, and that is this operation of composition that Jesus has defined here. This operation of composition is not complete, in the sense that not every pair of arrows can be composed. Right? So the condition that Jesus wrote here, that the domain of G is equal to the codomain of F, that's the condition under which a composition is defined. But if so this means that if you just have a random collection of arrows, in a graph, you cannot necessarily use those arrows to form a path. Right? The path has to satisfy sort of like a continuity kind of condition, right? So if you're going from A to B, you need a way to get from B to C, right? Etc.
Yeah.
And this, so the purpose of metagraph underlying the category is to give you this, is to give you the data, in a sense, on which to determine whether composition is defined or not.
Okay, very interesting.
Okay, then we go to the next. Okay, here is then our graphic representation of this. And when we present this graphical representation of compositions, we are thinking that there is a rule for building this kind of graphic. Then composition is the rule that says to us how we can build this graphic. Okay. And here some properties about identity. This property is the unit law. Then the idea here is that when we use the operation of composition, then we can include one operations that is the unit, and then to operate via compositions with another kind of arrow. Then identity is one arrow. And then there are two kinds of this identity can be understood, like a arrow that act on the left, or one arrow that act on the right in this operation. But you can see that this not act to the left and to the right in the same arrow, but only in different arrows that are composed. Then this can be represented in this way. This property says to us that we can first take the arrow F after the arrow identity of B. The index here says what kind of object are related with this identity. And then after we compose with G.
But of course, we could also draw that graph with a loop around B, and then you can eliminate just draw it differently. Just take B and have a loop, and then exactly the same picture, leaving out the B at the bottom. Then.
But here we have no loops. Because
or you call it the identity. You call the loop the identity 1B.
Oh, okay. If we say that the identity is a loop, okay, then you can drop this loop, or maybe better, you can say that the object B is a loop.
Exactly. Okay, very good.
Okay. And then these properties are present here like a tree graph. This was made only for emphasize how the identity operations can act in different ways. Here we go from this composition rule, and then we get these equivalent compositions. I wanted to put here in attached form the object B, because we cannot omit this object here. And then we have, in fact, here the composition.
So
Then,
again, we could just have loops be a directed loop. It could be either clockwise or counterclockwise, and you'd get an equivalent picture to that then.
but okay, we can think about the loop directed in counterclockwise or in clockwise, but you can see that this identity acts in different way. Here, this identity acts in this path, and here identity acts in this in another path.
Okay, yeah, okay, that's fine.
Mm-hmm.
So we could have two edges then connecting A and C together, and still you can make out an equivalent graph of that, what you're representing in those ideas there, I think, with just a loop around B and then different edges connecting A to C, I suppose. Well, yeah, that's interesting. Of course, I guess that's a theory in itself, equivalent graphs, the representations of an idea in category theory by different types of graphs.
Yeah. Okay, I wanted here to present in this way using tree graph, because
Okay.
I think that we can understand a tree graph like a kind of operations related with identity.
Excuse me.
Because we are here cloning this part of the graph, and this effect of cloning is it was made by identity. I think that in the next maybe we can okay, not here, but in the next we go back to this kind of graph. Here there is a property of composition that is associativity. In the category theory, it is supposed that the compositions either have this property, the property of associativity. We have not operation of composition without associativity in category theory. Mm-hmm. And this property is represented here in diagram. In fact, this is this kind of representation are called commutative diagram. Because we can find here equivalent cycles for getting the same results. Okay, and then this kind of property can be represented here with a inner-tree graph. You can see now here how the identity operations permit to us to replace these two arrows by one equivalent arrow here. The same is here between these two arrows are replaced by the identity C by this arrow.
So I guess it would be difficult to understand category theory without graph theory, right? There's no other way of talking about those ideas without drawing a picture, something which you're drawing right now.
Yes, but many people use category theory, the axioms of category theory, and not necessarily put a graph. No?
Well, that's interesting.
But okay, and here I am showing how identity can be understood in the opposite way, like operations that permit to us to go from one arrow and split into arrows. Here we have the same, and here we split this arrow into arrows. Oh. Mm-hmm.
So how many axioms do you need to define category theory?
No, like axioms only that we listed here. A metagraph with these two operations that have these two axioms. The unit law, that is that you can use the unit in these two ways, and composition. And only that you need for build the category theory.
So there's only what, 2 or 3 axioms completely define category theory then? That's what you're saying, right?
Yes.
Yes.
Mm-hmm. Mm-hmm. And is a powerful tool for working in mathematics. Mm-hmm. Okay, this are all that I was prepared for this presentation. Then the next, I wanted to speak about a higher order operations in category theory that are functors and natural transformation. But I have not enough time for building the slides. Then I can present in another session. Mm-hmm.
Yeah, I find this very interesting, actually. It gives me much more insight into category theory than I ever had before. So I appreciate that.
Okay. But thank you. And I don't know if you are maybe can take the time and present your paper.
Yes, I think that would be a very good thing if we could sort of, in effect, change subjects, since Dr. Sochik won't be talking specifically about graph theory, but I think we ultimately still want to to look for possible connections, but
Yes, the idea is a very, obviously graph theory is being used to describe ideas in category theory. Well, if there, I'm more directly looking for an application of geometric algebra or Clifford algebra to graph theory. And of course, that would translate over to certain ideas in category theory as well, I would imagine. You can be described, well, I look at geometric algebra, Clifford algebra as a way of doing calculations in graph theory, but ultimately, even in category theory, well, okay, you follow arrows around, but you are doing calculations of one sort or another that are why category theory is used as well. Okay, so maybe I'll share my screen and show you these ideas I have about geometric algebra or Clifford algebra. So let's see if I can do it efficiently here. Let's see here. Yeah, can you see my my slide, or maybe it's not on there yet?
Not yet.
Okay, let's see if I can fix it. Can you see it now? Maybe not.
No.
Let's see how to get there. Let's see here.
Green button that you can use for change.
Oh, okay, I can see it now, I guess. How about that now?
Now we can see. Okay.
Okay, that's good. I'll try to enlarge it here. Okay, so you can still see it all right. Can you see it? Calculus of compatible nilpotents?
Yes.
Okay, that's good. Okay, so again, these are the definitions I gave, I don't know how many times already, but that's just this is the multiplication table of what I call compatible null vectors. So you see it's very simple. And the other one is the other for negatively compatible. That simply means, well, that this relationship is true. AI times AJ plus AJ times AI is equal to 2 times the inner product of these of AI and AJ. In particular, you see that AI times AI are all nilpotents. AI times AI nilpotent, AJ times AJ for any I and J. So I'm picking a set of N, well, N or N plus 1 nilpotents, any 2 of them which satisfy the same multiplication table. That's for positively. And of course, if you choose a negative sign instead, then you have this multiplication table. So you can see there's still nilpotents, but in this case, the multiplication AI, well, for example, AI times AJ AI is equal to minus AI. So again, AI times AI, AJ AI becomes minus if the nilpotents are negatively correlated. And that simply
Can I
means that
ask
this,
just wanted to ask one sort of technical question, since we were talking about sort of technical issues in graph theory and category theory. Here in your definition number 1, you write inner product, but is that an essential part of the definition? I mean,
well, that's from geometric algebra, Clifford algebra. You always, you separate the product of any two vectors into a symmetric part and an anti-symmetric part. So AI dot AJ is a symmetric part. Well, it's 2 times the product.
But here you're not actually talking about Clifford algebra yet, right? You're talking about.
Well, actually, this rule here gives you the fact that, well, you can see the multiplication by assuming this algebraic property, for example, equal to +1, we get this multiplication table.
Yeah, no, that's okay. But I was just saying, could I dispense with the notion of inner product altogether here, at least at this point, right? Where, because the algebraic quantities that we're talking about here may not necessarily be related to a metric.
Okay. Now, this is the interesting idea, is that the inner product really, that's right. We can think about AI, this relationship as being a kind of a duality operation. The only difference is that for ordinary duality of vector spaces, you don't have AI AJ plus AJ AI equal to 1. You just have AI operating on AJ is equal to the delta function itself. So, but that's the idea, though. If you assume this idea of duality, then arising from that is the geometric algebra of the Lorentz signature 1n.
So I guess my only point is that at this point in your presentation, I prefer not to introduce the notion of metric, and so therefore not.
Okay, I can understand that actually.
Product, right?
That's right. So, but if we only talk about nilpotents, but you see, saying what I'm trying to explain is that saying that this relationship is true, AI times AJ plus AJ times AI equal to just 1 in this case, it implies a metric really, and that really follows from this relationship. In fact, that's what I'm saying here. If you assume a positive sign, okay, so you start with a set of nilpotents. You assume that you don't even, as a minimal axiom, you're really only assuming that one relationship, but that will imply anti-commutivity. So a Grossman algebra also arises from that definition, the 2 definitions I've talked here. So if you just take +1, let's not talk about the negative sign, because just talk about this relation. You start with a set of nilpotents, A1 to AN, and you assume that any pair of them satisfies this relationship, AI times AJ equal to plus AJ AI is equal to 1. Then actually that's also defying the Grossman algebra as well. It follows from taking the sum of, you take A1 plus A2 and you square that, then you'll see you have to get, and you look at A1 plus A2, consider that to be one element, and then A1 minus A2 equals a second element. Though by the same rules here, you'll find that A1 plus A2 anti-commutes with the element A1 minus A2. So this one relationship saying is equal to +1 implies that there are elements now in this algebra of nilpotents generated by n nilpotents, which all have square 0. Then you get the rules of Grassmann algebra built into that then.
Mhm.
So I'm saying this table really encompasses the idea of a Grassmann algebra as well. When you take pairs of these things, I'm just telling you how the basis vectors multiply. They're all nilpotents. That means that the table down the diagonal is all zeros. AI times AI is 0 and AJ times AJ is 0. Okay, but if you take AI times AJ using that rule, you find that's an idempotent. And AJ times AJ times AI is also a nilpotent. Whoops, AI. Yeah, AJ times AI is equal to AJ times AI. That means it's a nilpotent then. So when you define this simple relationship, AI times AJ plus AJ times AI is equal to 1. Forget the inner product. That really comes by assuming these are vectors, and we're interpreting it as vectors, and then that is a Clifford algebra relationship as 2AI dot AJ. So that says that the inner product is equal to 1/2 in the associated Clifford algebra. But so in a certain sense, by defining this multiplication table, you are defining the Clifford algebra G1n.
But my point, I guess, only is that it's sort of premature to use the notion of inner product.
Well, that's right. You're correct there. And I should actually develop that more. Just start with that relationship and show how the idea of a Grassmann algebra. Okay, well, see that's the Grassmann algebra generated. We assume that you'll see that E1 times F1. E1 is just equal to, where do I define it here? Yeah, so E1 is just A1 plus A2. And F1 is A1 minus A2. If you calculate, you'll find that E1 times F1 is equal to minus F1 times E1. Well, that's, of course, Grassmann algebra we're talking about then. So by assuming that one relationship, then we are justified in saying that that really generates, this one relationship here generates the notion of anti-commutativity as well as the notion of a metric, namely the metric of the Lorentz metric G1n. Now, if you simply change the sign for table 2, so that's why I'm identifying the geometric algebra G1n with what I call the compatible nilpotents, which have positive compatibility, namely 1 AI, the commutativity relationship A1 times A2 plus A2 times A1 is equal to 1. Well, so this is a way now of defining the standard basis of the geometric algebra G1n in terms of these nilpotents. And we can successively add more and more. If you expand the algebra of AKs, all of the inner product, well, now we're thinking about the inner products are all equal to 1/2 or minus 1/2 for the negatively correlated null vectors. So this relationship, how to define that was extremely difficult for me to find this relationship actually, but that allows you to extend this by just starting with a set of nilpotents, all of which have squares 0, but satisfy that compatibility relationship A1 times A2 plus A2 times A1 is equal to 1. That really gives you this geometric algebra 1n then. Well, that's for n. We see A1 up to AN plus 1 nilpotents then. So by extending the real number system by compatible n plus 1 compatible nilpotents, satisfying that relationship, you get the geometric algebra with the metric 1, n. Okay, and that's, if you change the sign to negative, then you get this other one, n, 1. Okay, but now what I want to show you, okay, well, we're just taking a change of basis in the geometric algebra 1n. So I've written that table down again, which is interesting. And so we're just going from now the algebra of nilpotents to the algebra, the standard basis of the geometric algebra with Lorentz signature 1 comma, well, up to 1 comma 7, okay? And then you take the inverse of that matrix and you get this. Okay, so the only thing I wanted to talk about today is against these gradient operators then. Defined in terms of the new basis of the Lorentz signature. I'm only going to look at positively correlated so you can forget the negatively correlated ones. So I call that the algebra of nilpotents generated by n plus 1 nilpotents, A1 up to an plus 1. And that's really equivalent to just choosing a non-standard basis. The standard basis of the Clifford algebra G1n is exactly E1, F1, F2 up to Fn up to Fn. Okay, just the notation I'm using here. Okay, so that's the rule of positively compatibility of nilpotents. But you can see, cross that out of here, and it doesn't look like a metric relationship, but it actually generates a metric relationship. And that's why I'm able to put equal to 2ai.aj, although that's in Clifford algebra now. That's in the geometric algebra G1, Lorentz signature then. But now you can see I'm just taking ai plus aj, this multiplication table, just multiply it out using the standard rules of associativity. You get ai squared plus aiaj plus ajai. Okay, well these are 0 and you get equal to 1 then, using that compatibility property. Okay, now I like to define the gradient operator in this algebra. Normally, people use it, for example, the Gibbs Heaviside use the Euclidean space G3, okay? You know, just the usual metric of quadratic forms with signature 3, okay? So that's the standard way people define the gradient operator in Gibbs Heaviside. But now I'm going to define the same gradient operator in the Lorentz signature G1n. And there's a definition. Notice that I changed the sign. I have E1 partial derivative with respect to S1. I'm distinguishing that from and then, so the position vector using the usual metric, x is equal to S1 E1 plus Si plus 1 Fi is defining the position vector in the Lorentz signature in the geometric algebra G1n. Okay, but notice that if I take the gradient operator of x in 3 dimensions, or when n is equal to 2, we just get the standard divergence of the position vector in Euclidean space. But now I want to define it using this geometric algebra, not the standard Euclidean space. But I still want it to have the same properties. Delta, the gradient of x is equal to n plus 1, okay, because we have, that's the signature of our we have n vectors, okay. So that's just a change of basis. So the gradient operator still has that property. And I do that by defining the gradient operator E1 partial S1 minus that with respect to this basis. But now you see, I want to relate this gradient operator, which is just the standard gradient operator, but in the Lorentz signature with the standard gradient. So I define now what I call the null gradient, and I put a hat over that. And I say AI times partial with respect to this basis. Now you see my x now in this basis now is just I equal to 1 to n plus 1 of xi ai, okay? But you can see now with that definition, if I apply this gradient operator to x, I'm going to get 0, right? It follows that the gradient of x is 0 because if I take partial I of X, I just get AI, okay? So obviously then this hat gradient dot X is 0. But again, well, that it also says that the outer product, the wedge, instead of, in the cross product in Clifford, in the usual Gibbs Heaviside gradient operator, the cross product of X, the position vector is 0. Well, that's a corresponding relationship, but expressed in the Lorentz metric. But now we have a second type of gradient operator, which is interesting. Okay. I define what's called the additive dual sum gradient. So what this means here is I'm taking this gradient. So this one, the hat gradient, is just AI partial with respect to xi, because I'm defining my position vector as equal to xi times AI. Okay. It's just a different, in the standard basis, we have the usual Lorentz, the usual orthonormal basis in the Lorentz algebra, 1, comma, n. Okay, so here I'm doing the same thing now, but this the interesting thing. I'm taking, in a certain sense, that's a kind of a dual operation. The dual of AI, I'm defining equal to, okay, I define an plus 1 as just the sum. Let me go back to where I define that so you can see it. Where do I define it? I guess I define it. Where is my A defined here? So I want to write an as just the sum. You see, an, this is A4, is just A1 plus A2 plus A3 plus A4. If I take the dual of A3 in A1 plus A2, you just take away, so that's just A1 plus A2 plus A4. So I don't see it where I define my A here, but an plus 1 just means take the sum A1 plus A2 plus A3 up to an plus 1. Okay, so when I'm taking the dual as a sum, I call it, I'm just taking A4, which is A4 means A1 plus A2 plus A3 plus A4, and subtracting A3 from it. So I get A1 plus A2 plus A4. Okay, now I define this new scalar differential operator. So when I write partial parentheses n plus 1, I mean take the sum of all the partial derivatives, partial x1 plus up to partial xn plus 1. Okay, but now I want to calculate, let v be the vector. It's just a position vector using the basis of these null vectors, which all have inner product 1/2. Okay, so v is just v1a1 up to vn plus 1 an plus 1. If I take v dot, the sum of all these a's, I get this formula. Well, but now you see I'm introducing this new notation. If I put a hat over a vector, that means I'm taking all the scalar components. Okay, those are the v1a1 plus vn plus 1 an plus 1. I'm taking the components that are not equal to, if I take take the hat, or the, whatever you call it, over v, I mean the sum of all the components of this vector here. And so it's an abusive notation that can be confusing because I've used the same notation. That's a vector, okay? So its dual is a dual in the A1 plus A2 plus A4. That's a vector, but here I'm using the same notation. I'm abusing notation by writing the dual of v, this vector v is a scalar now consisting of the sum of all the components, V1 up to Vn plus 1. So it's kind of like a trace operator in a sense. Okay, and the dual of V hat I, on the other hand, I leave out the ith component and take the sum of all the other components here. Okay, I admit that notation's a dual. It's a abusive notation, but you know, things get out of hand if you don't introduce such notations there. That's the idea. Okay. And I try to explain that, whereas V is a vector, its dual V hat is a scalar, but both VI and VI hat, or inverse hat, I guess you'd call it, are scalars. Okay, so now, okay, so what's new here, the most important thing of what I wanted to tell you today is, in which I'm not able to do, I wasn't able to see this relationship before. We're going to use this dual notation introduced in 9 to express the geometric product of two vectors V and W in this algebra of nilpotents consisting of compatible n+1 nilpotents, which are compatible in the sense that they satisfy that table 1. Okay, so any pair of the inner product of any pair now is equal to 1/2. The interesting thing now is we can represent the geometric product in this way. Well, by definition, remember, I could write the inner product by 1 minus delta ij plus the outer products. That's the usual outer product. No change in this definition. But when I write it now, I'm just doing algebra here, binomial expansion type things. And what we get is that V dot W is equal to this relationship. Notice that these are the duals. So that's a scalar, and minus this thing here. Well, again, this is just pure algebra. I will explain it in more detail in a more detailed version of this. I've had a lot of trouble doing these calculations because it gets extremely confusing using this basis, but it seems to be an extremely interesting basis because in a certain sense, all the rules of matrix algebra follow from by taking this Lorentz metric in a geometric algebra, really. But it's just a change of basis that we're looking at. But the outer product, that's just the usual outer product of Grossman algebra. So, okay. Okay, now in the sheet I sent you, I actually updated a little bit. I want to show you, notice in this expansion, V dot W in this basis of nilpotents, that this is the interesting part, we get VI times WI. Well, that's like the Euclidean inner product of n+1 vectors, right? Because it's just the sum of the components VI, WI from I equal to 1 to n+1. So if we solve that for this expression, I'm defining a new inner product on the basis of these nilpotents, okay, on the basis of the A's. Okay, so I'm defining this new inner product by I equal to 1 to n+1 of VI, WI. Well, that's exactly this term here. But, okay, so this is not in what I sent you. I updated my document since I sent it to you just last night, I guess. It's better to look, or a couple of days ago, I guess I sent it. So that's the same thing as this dual minus 2V dot W. That's just the inner product in the usual geometric algebra 1, n. Okay, but you can represent this new inner product in this way. It's V hat, W hat minus, that's almost like a relationship with the outer product. You see, that's what I'm getting this from. So VW is 1/2 of this plus this. Okay, that's the standard outer product. That's the Grossman outer product. but now in a certain sense, this inner product is looking like is just the symmetric part here. But notice that it's a minus this thing plus that. Anyway, so I'm defining a new inner product on the what I'm calling the star geometric algebra n+1 by defining V star W is equal to this new inner product plus V wedge W. And well, that we can write it in that form. Or another way of looking at it, which you don't have this 14, it's a new 14. What I sent you is not the same as this, but that the interesting thing, we can write this geometric algebra, which is the geometric algebra of Euclidean space, in terms of the Lorentz signature by using this idea of duality of the components, the sum, dual sums, if you like to call it, minus 3 times the usual Lorentz inner product. And now VW here is the standard inner product in the geometric algebra 1n. But so I'm defining the new that's really the geometric algebra n+1, the Euclidean space, arising from the Lorentz signature by simply modifying the inner product, the definition of an inner product. The Grossman algebra is the same, though. Well, anyway, these are just formulas that took me a long time. Calculations are extremely confusing, but notice this. If I take the sum, remember that partial n+1 means you take partial x1 plus partial x2 up to partial n+1, and you apply it to x, you get a n+1, because remember, a n+1 means take the nilpotents a1 plus a2 plus up to a n+1. Okay, so I've never seen these calculations done before, but this new scalar differential operator, the sum of all these partial derivatives of x, gives you a n+1. And if you take the inner product of a n+1 with this gradient, notice that when I transform over to the Euclidean inner product, this hat nabla becomes a standard gradient in n+1 dimensional Euclidean space. So notice that in Hestenes' space-time algebra, it's reinterpreting what we mean by in one frame inertial system. What's a bivector? Well, for example, electromagnetic field in one inertial system or an electric field looks to one observer just as a plain electric field in a station, in a rest frame. But if you take a moving frame, that electric field then looks like an electric field plus a magnetic field, while a magnetic field is represented as a bivector field. So it appears to me that this could be important in the sense that it gives you a different interpretation of elements of a Euclidean space in terms of its corresponding Lorentz space, Lorentz metric space. And of course, that's extremely important in relativity theory, where you have rest frames, inertial systems, and you have moving frames. And what's an electric field in one frame, in a moving frame, consists of an electric field and a magnetic field. Okay, so I'm just trying to develop the calculus now in this special algebra of nilpotents, of what I call compatible, positively compatible nilpotents. Okay, so here I have these two types of, that's what I call it, a null dual sum gradient, and this is the null gradient. So I'm just developing formulas for these gradient operators, which were extremely difficult to get because of the confusing calculations involved. But again, you can reduce it to just rules, and then the rules, of course, after you figure out one time, you don't have to struggle with it so much. But to getting a consistent set of rules, well, I had to introduce this new additive differential operator of all the partial derivatives. For example, if you do it in Euclidean space, that's be the same, taking partial x plus partial y plus partial z, considering that as a differential operator. That makes sense in this algebra of nilpotent, compatible nilpotents, but we don't use that. We use a directional derivative. Well, you still have directional derivatives, and that's what I'm defining now in the dual sum in this algebra of nilpotents, compatible nilpotents. So I'm just trying to work out these relationships. Well, the interesting thing is, of course, the fact that here you see n plus 1 times n over 2. Well, that becomes important because that's just the binomial combination of two things taken, n things taken, or in this case, n plus 1 things taken 2 at a time. So that arises now with this other type of gradient operator I'm defining. But the standard gradient operator still, okay, well, I'm just writing down these. Okay, this relates to standard gradient operator in terms of this dual, this gradient operator with respect to the nilpotent bases, compatible nilpotent bases, positively compatible nilpotent bases. So you see, well, it becomes easier to do these calculations. I'm going to check more of these to make, I need to expand this because it's just a summary of the formulas which I've painstakingly developed over the last 6 months, basically. I've struggled with these calculations because maybe I'm just getting old, but I found them to be extremely confusing. But I hope that I've got these formulas correct now. But again, they're just formulas. I'm expressing the Laplacian now in terms of these in the Lorentz spaces, the standard basis. Well, no, this is in the nilpotent basis of these operators. So I'm just trying to. Well, that's the thing. Again, this slide is different from I can send you this new version. This last page is page 7. You don't have. I don't think you have page 7. You only have page 6. But this is representing the Laplacian in the Lorentz metric of space-time in terms of the Lorentz metric, really. If you think about it as a Clifford algebra, as a nilpotent algebra, well, you can see that's the thing. I believe that there's too much emphasis put in on this idea of a metric. In fact, that's why I like to quote, when you interpret a Clifford algebra, what an element in a Clifford algebra in different inertial systems, then you're really mixing the notion of vectors and bivectors. You're reducing it to just anti-commutativity relationships versus commutativity relationships. So I hope this also throws more insight into the structure of Clifford algebra, and I hope that we can employ it for graph theory, because you need what the idea is you're trying to algebraitize operations in graph theory. Well, but since we use graph theory to represent ideas in category theory, but to do calculations in graph theory regarding edges, the number of edges, for example, well, you can see the number of edges of a complete graph, which has n plus 1 vertices, exactly partial, the binary formula of n plus 1 things taken 2 at a time. And that arises in these derivative operators. Well, this one reduces to 0 if you take the hat gradient of the position vector, you get 0. But in this alternative one, where you're using the dual being a dual sum type idea, you get the formula for the number of vertices in a complete graph. So I hope that that's about all I have to say, I suppose. So any questions or comments?
Oh. One first question was just are we starting with the standard definition of gradient? That, but I do not I can't find the definition of derivation here, for example. But in the way that after we can think about the gradient operator, and I believe if the properties of the convergence algebra can take to introduce the derivation operation.
I'm having trouble understanding you. You're breaking up. I'm not sure if it's on my side or.
Yeah, also the.
Bill, are you having trouble understanding? Is it clear? Is this audio clear to you?
No, it's also a little fuzzy and perhaps too loud.
Okay, maybe if I close my screen now, so I stop sharing, maybe it'll help things here. Yeah, I'm having trouble understanding. Everything's garbled for some reason.
Yeah.
Is that on my side? Am I garbled?
No, you're fine, Dr. Sobchak. Dr. Cruz is sort of, the audio is intermittent.
Yeah, I'm having trouble understanding.
I still can't hear either. No, also.
Yeah, you're very garbled. Okay, I guess he's still having trouble, but yeah, I would like to continue. I think I still have hope that these ideas can be fit together in some way. The graph theory, not so much maybe, well, where Clifford algebra would be useful in category theory is exactly where graph theory is useful in category theory for certain ideas, which can be represented, and which I hope we can represent using. Well, there is more work than just mine. This idea from this MIT professor that used Clifford. Well, Clifford algebra is used for edge, calculating edges and all this stuff, but she does it in quite different ways than what I'm trying to do here.
Well, I guess when I look through your paper, I got a little, my first sort of reaction is going through the paper, I got a little lost with the different types of gradient operators. Thank you.
Yeah, that's very interesting, really, because that's what you need if you go to a Lorentz, representing the idea of a gradient in a Lorentz metric. But the Dirac the Dirac operator, you change the sign. You go plus, minus, minus, minus when you write the gradient operator. If you think about it in 3 dimensions, that's probably the best idea, where you have one plus 1 minus 1 minus 1. You want to represent the gradient operator, like in Gibbs Heaviside. Usually you represent the gradient with 3 vectors which have square plus 1, or the inner product is 1. And of course, the geometric algebra G3 is you represent it in terms of the Euclidean metric, but you can also represent the gradient in terms of +1, -1, -1, just by changing, so that the gradient of the position vector is still 3. It just, the gradient operator counts the dimension of the space, of the divergence, counts the dimension of the space. And that's exactly the same thing for the Lorentz. When the gradient operator is expressed in the Lorentz metric, it counts the dimension of the space. So if you're a Lorentz space n+1 dimensions, then that means that gradient in n+1 dimension is equal to n+1, because it just says a Euclidean gradient, it's counting the dimensions of the space. So you have to, you're just expressing the same properties, but using the Lorentz metric instead of the Euclidean metric. But the gradient operator still counts the dimensions of the space, the divergence, or the dot product, inner product in Clifford algebra counts the dimensions of the space that you're in. And that also applies for the negative signatures as well. For, you know, if you have n+1 negatively compatible null vectors, then you're talking about the Clifford algebra G n, 1. So still Lorentz metric, but you're, instead of plus, instead of minus, plus, you're using plus, minus. It's still a Lorentz signature though. So maybe we can continue. I will expand these ideas more using just the 3-dimensional case, because you can see it better than.
Yeah, perhaps some examples would help.
Yeah, there's lots of things. That's the thing. There's just, first of all, I wanted to get the formulas right because calculations become, it's very confusing. If you have the inner product of all these null vectors is 1/2, which is pretty strange, but only possible because you're using a Lorentz signature. But then you can relate it back to the Euclidean metric, which is by a simple formula, which is pretty strange, but I think it's very interesting. Maybe Jesus is back. Can you understand us now? Is your audio all right now?
Yeah, I can listen to
Maybe there's too much volume. You're still broken up here. You turn on your volume. It's too overloading it.
Now is better.
Yes, much
Yes,
better.
much better.
Okay, your volume is up too high. That's the problem, I guess.
Oh, okay. The problem was no. I wanted to
So turn it down a little more, even. Turn your volume down a little more. Your mic volume, I guess, is too high.
Higher.
Lower.
Lower.
Lower. Okay.
That's
now
good.
Perfect.
Oh, perfect. Okay. And I wanted to comment about the definition of gradient operator, because I like it to see the definition of derivation based on Clifford algebra properties.
Okay, so I would be willing to talk about that next time. We probably don't have much time today, but I'll just look at 3-dimensional space, maybe, and also 4-dimension, because that's space-time. So that's n equal to 2 or n equal to 3, and I'll work out formulas exactly and compare it to the usual Gibbs Heaviside gradient, where the divergence is equal of the position vector is 3, and so on. I agree that's confusing, because it's never really clear, even in relativity theory, that the gradient operator really is just copying the gradient properties of the gradient operator in 3-dimensional Gibbs Heaviside. It counts the gradient, the D'Alembert is just count the divergence of the position vector using the D'Alembert is just 4. It counts the dimension of the space, just as the gradient operator in Euclidean space divergence counts the dimension of the space. And and the cross product, in vector analysis of the position vector is 0. Well, that corresponds to the wedge product is 0 for the gradient operator, and it's exactly the same when you do the gradient operator using a Lorentz signature. So that's what I'll try to work out next time. It should be very clear. But that's the interesting thing, that other gradient operator, which is a dual, what I call the dual sum, gives you the formula for n+1 things taken 2 at a time. Well, that's the same number of edges in a complete graph, so, which is interesting.
Yeah.
But is this the gradient operator in a general sense? Is it for example, satisfying a Leibniz rule of some sort?
Oh, yes, exactly. Of course. And a directional derivative corresponds exactly to the usual directional derivative. Usually people write, they use, again, this duality space that, they consider a vector and its dual is a partial, they represent a directional derivative using a partial derivative. But that's the whole thing that confused people about what Hestenes and I mean by a vector, a vector manifold, okay? Usually people, represent directional derivatives in differential geometry as a partial derivative, but we represent it just as like they do in Gibbs Heaviside by taking the dot product of a vector with the gradient operator gives you the directional derivative. E1 dot the gradient gives you partial x1 or partial x. E2 dot the gradient gives you partial y, and so on. So that's what's confusing people with this idea of a vector manifold, my book with Hestenes was rejected. The publishers wouldn't touch it for 10 years. It took 10 years for our book, Geometric Calculus, Clifford Algebras to Geometric Calculus, Unified Language for Mathematics and Physics, to be accepted for publication. It was only really because of Professor Lunesto that it was finally accepted for publication. Before that time, it had been rejected for 10 years. But still, people don't really, well, a lot of work has been done now. Well, you have the Clifford analysis group, which developed the gradient operator in n-dimensional space. But again, that's considered a separate group in Clifford algebra, the Clifford analysis people, because they've highly developed. I should probably look more at their work too, and just trying to keep these ideas straight, But anyway, as you know, mathematics has exploded, and even Clifford analysis and standard Clifford algebra geometric algebra has exploded in many different directions now. But computer scientists are using these concepts. And that this conference in Denver had more people that were using these ideas than in the standard mathematical differential geometry is still the standard usual definition of duality, and a vector is partial derivative, a directional derivative is a partial derivative, and so on. But they're really compatible, as we try to point out in our book, my book with Hestenes ideas. So
okay, well, maybe we can take another crack at this in 3 weeks, I guess.
I am really interested in these ideas of graph theory that Hayes has been, as you too have emphasized. Category theory is not really for doing calculations per se, but you use graph theory, and graph theory, you need to do calculations with graph theory. Count the number of edges, or whether two edges are connected, or a loop, or whatever. You do calculations with graph theory, but as you pointed out, category theory is really more just conceptual ideas and relationship between not just plain set theory, as you pointed out.
Yeah, I think it wouldn't be correct, I think, to conclude that you don't do calculations in category theory.
How do you do calculations in category theory?
Well, it depends on what you mean by calculations. Of course, you can prove theorems in category
That's right. You
theory.
can take the composition of elements in algebra just as you take the composition of functions. There's not much difference really. In fact, you can represent those ideas. Composition of functions is the same thing as composition of elements of a graph.
But you can build different categories from the more elementary categories. And in this process, it is very important because you can get more complex systems. I don't know if we can say that we are doing there some kind of calculations, but in fact we can build more complex categories and look for their properties, and then the degree of generality of this can after we use it in some in different applications. In fact, there is one a tendency to use category theory in computer science, for example. The
Interesting.
the idea of object-oriented programming was based in the in category theory. Then the class of objects and the programming. There is a computer language using category theory for programming. Then it can be a powerful tool for calculations of some kind of problems. Then I think we need to.
I'm beginning to think that computer scientists are way ahead of mathematicians and everybody else, because mathematicians, computer scientists use Clifford algebra to do calculations, but mathematicians, again, Clifford algebra has not been recognized as a universal language yet, although Grassmann algebra has been. Somehow the view of the Clifford algebra, geometric algebra community, mathematicians have not accepted it widely, as computer scientists have also accepted. Now you're telling me they've also accepted category theory, so they're ahead of mathematicians then.
Yes, it could well be. So shall we agree that we'll meet again in 3 weeks? Shall we at that time concentrate primarily on this development Clifford algebra? I feel like I need to focus more closely on this new paper by Dr. Sobczak. It doesn't. I feel like I'm only skimming the surface, and I don't really quite appreciate the points that that you're making. Maybe just because I haven't had enough time to work through the details. But I think, as I mentioned, a few examples might help.
I'm not going to restrict myself to 3 dimensions, but I think that the application to graph theory is extremely interesting, and of course I'm interested in the category theory part too. But so I like to continue. Well, I'll stick to 3 dimensions, or maybe 4, because 4 is extremely important as well to understand the power of geometric algebra. That's why Hesnes has been so successful, because physicists, well, again, a limited community of physicists have adapted geometric algebra. But I've been working in it now, what, 50 years or more now, and it's still not universal. I don't think all mathematicians know what a Clifford algebra is yet. Mathematicians generally focus on well-known problems, and anyway, whatever.
Okay, well, let's meet again in 3 weeks, and we could perhaps repeat the same format. I mean, if Jesus, you felt like you wanted to continue your lecture on category theory and graph theory,
Okay.
maybe we would just continue the same pattern, and eventually we would find a common basis. But I think it's okay. I mean, if
Yeah, so it looks like complete graphs are what's most promising with what I'm doing, because like I say, that one of those gradients gives you the number of n+1 things taken 2 at a time, and that's of course the number of directed edges in a complete graph connecting vertices, n+1 vertices. Yeah. Anyway.
okay. All right. Well, let's see each other again in about 3 weeks. Well, in 3 weeks exactly, and we'll continue.
Okay.
I look forward to receiving an updated version of your document.
Yeah, it's just the last page. It's interesting though. I'll send it today.
Okay.
Right
Great.
after it's very easy to send, of course.
All right. So,
Okay.
bye for now.
Well, it's been very interesting. Thank you very much, both of you.
See you in 3 weeks.
Yeah,
See
sure.
you.